Okay, so let's go ahead and take a look at this objective. So this objective has a few things in there. It's got 45, 45, 90 triangles. It has 30, 60, 90 triangles. And it has sine, cosine, and tangent. So with a 45, 45, 90 triangle, what's unique about it is the fact that it's an isosceles right triangle. So I'm just going to look at this for a second. If I label one side X, right, and then I label my other side X, then what ends up happening is I have x squared plus x squared is equal to c squared. So then 2x squared is equal to c squared. And so I get 2x squared in the square root is equal to c. And then you get x root 2 is c. And so that is where this x root 2 comes from. So that's why the triangle, the 45, 45, 90 triangle theorem works, is because of Pythagorean theorem. Okay, so now when we look at finding the values of x, my hypotenuse side here is the same thing as the side length times root 2. My side length that I have is 4, so x is going to be equal to 4 root 2. Okay. Now here, again, side length times root 2. So then x is equal to 5 root 2. That's my side length times root 2 again. So I get 5. And then I multiply the two 2's underneath the root, and I get root 4. Square root of 4 is 2. So then 5 times 2 is 10. So now, 30, 60, 90 triangle. I'm only going to look at one of these here. And you do have to memorize your ratios. So if you wanted to, we could draw it differently here. So if I had 30 here and 60 here, my root 3 side is here, my x side is here, and my 2x side is here. So why does this theorem actually work? Well, it goes back to the whole idea of a equilateral triangle. So if I draw a 60, 60, 60, right, equilateral triangle, and I label every single side x. Okay, if I drop a perpendicular bisector, then what ends up happening is I create two 30-degree angles here and a 90-degree angle on each side. Well, a perpendicular bisector means that each side line down here is x over 2 because it splits it in half. So the bottom side is x over 2, and my hypotenuse is x. Then I can solve for my height, which is my b. So by the Pythagorean theorem, x over 2 squared plus h squared is equal to x squared. So x squared over 4 plus h squared is equal to x squared. Subtract this x squared over 2 to the other side here. So I get h squared is equal to x squared minus x squared over 4. Find a common denominator. So that's 4x squared over 4 minus x squared over 4, which gives me 3 of them, x squared is over 4. And then when I try to solve for h, I square root both sides. So I square root, so I get 3x squared over 4. This simplifies by roots. I can separate out my roots. And so I get root 3 root x squared over root 4. Square root of x squared is x. This is root 3. And then square root of 4 is 2. So now this side is x root 3 over 2. And I don't like all my denominators of 2, right? So if I wanted to preserve my Pythagorean theorem, I can multiply everything by 2, and that's where I get my 2x from. my x times root 3 is now not over 2, and then my x is not over 2 either. And so that's why the 30, 60, 90 triangle theorem works. In theory, the reason why it also works is because this triangle on the right is congruent to the triangle on the left. And that is pretty easy to prove that they're congruent. Okay, but we don't need to necessarily do that. Okay, so now if I look at this, my hypotenuse is my y. My 30-degree angle, so this 12 is actually the same thing as x root 3. So 12 is equal to x root 3. So then x is equal to 12 over root 3. And so I do need to get rid of the roots in the denominator. So I multiply top and bottom by 1. Fancy 1. It's root 3 over root 3. So I get 12 root 3 over the square root of 9. Square root of 9 is 3, so 12 root 3 over 3. And then my 12 and my 3 reduce, so I get 4 root 3. So that's my x. So x is equal to 4 root 3. And then to find y, I just have to double x. So y is equal to 2 times 4 root 3, which is 8 root 3. So y is 8 root 3. Okay? Again, find the value of x and y. Here's my 30-degree angle. So this 15 is the same thing as x root 3. So x root 3 is equal to 15. So x is equal to 15 over the square root of 3. Rationalize the denominator again by multiplying by root 3 over root 3. So I get 15 root 3 over root 9. So I get 15 root 3 over 3. And again, my 15 and my 3 reduces, so I get 5 root 3. So x is equal to 5 root 3. Now y, my y here is the same thing as 2 times x. So that's 2 times 5 root 3, which is 10 root 3. So x is equal to 10 root 3. So now we're going to do sine, cosine, and tangent, which sine is opposite over hypotenuse, which is why we write SOHCAHTOA. So opposite over hypotenuse, adjacent over hypotenuse, and then opposite over adjacent. Okay? So when you look at it, if I want to find sine of r, so difference between finding r versus s is if you look at r, my opposite and my adjacent sides are going to change. So here, when I look at r, my r is going to be, my opposite side is going to be here, where 16 is, and my adjacent side is going to be my 30. And then my hypotenuse is my 34. So when I look at sine, sine is the same thing as opposite over hypotenuse. So sine of r is equal to 16 over 34. And I do want you guys to reduce it. So both of them are divisible by 2. And so I get 8 over 17. Then cosine of r is equal to adjacent, which is 30 over 34, which is 15 over 17. And then tangent of r is equal to 16 over 30, which is 8 over 15. Okay, so now I will change this to s. Okay, and now my opposite side changes. And then my adjacent side changes. So sine of s is equal to 30 over 34, which is 15 over 17. Cosine of S is equal to my adjacent, which is 16 over 34, so 8 over 17. And then tangent of S is equal to 30 over 16, which is the same thing as 15 over 8. Okay, so that's my sine, cosine, and tangent. And they are different depending on, or kind of flip-flopped, because of the way that my adjacent and opposite sides work. Okay, so now I want the sine of A, but I don't know what my missing side length is below. I don't care what letter you call it. You just can't call it the hypotenuse, which is C, when you use the Pythagorean theorem. And don't use the letter I, obviously because of imaginary numbers. But I do need to figure out what my side length is. So A squared plus 7 squared is equal to 39 squared. So A squared plus 49 is equal to a big number, 1,521. And then I'm going to subtract 49 from both sides, so I get A squared is equal to 1472. Square root both sides. Oops. And now this breaks down. My A is root 4 times root 4 times root 4 times 23. So I broke it down by 4s because, you might have been able to break it down by 64, but I probably wouldn't have been able to do that without a calculator. So I would have just broken it down easier by 4s and just keep trying to break down by 4 or 9, which are perfect squares. Okay, so then I get A is equal to 8 root 23. So now I'm going to go ahead, I'm going to find sine. So sine of A is 7 over 39. That's nice. It doesn't reduce. Cosine of A, which is also nice, is 8 root 23 over 39. It doesn't require a lot of effort because there's no root in the denominator. The issue is when you get tangent of A, which will be 7. Look, dinner's ready. Over 8 root 23. And what you're going to want to do is rationalize the denominator. When you rationalize the denominator, you're multiplying by the same square root. So square root of 23 over square root of 23. We don't multiply by the 8. We only multiply by the root. So I get 7 root 23 over 8 times 23, which 8 times 23 is 184. So 7 root 23 over 184. And that is all 3 of my answers. Okay, my last example here is if sine is equal to opposite, right, over hypotenuse, and I'm given my opposite side is x minus 2, and my hypotenuse is x plus 4, then I could say that 1/2 is equal to x minus 2 divided by x plus 4. And then to solve this, we cross multiply, so x plus 4 is equal to 2 times x minus 2. And then I distribute my 2, so I have x plus 4 is equal to 2x minus 4. So then 8 is equal to x. And that is how I solve for x there. And that is it for this lesson.